Hello everyone, I am Shanmuramanan, Assistant Professor, Department of Mechanical Engineering from Pondicherry College of Engineering. Last class, I thought the problem based on linear bar element. Today, I am going to teach you the problem based on taper bar element. So, read the question. That is the problem number 4. Using two finite elements, find the stress distribution in uniformly tapering bar of circular cross-sectional area is 3 cm square and 2 cm square at their ends. So one end is 3 cm square, that's 3 is a larger end and 2 cm square is a smaller end. Total length is 100 mm. Subjected to an axial tensile load. The load acts along axis, then that load is known as axial load. And in a one-dimensional element, the axial load is act, then that one-dimensional element is known as bar element. So axial tensile load of 15 Newton at smaller end and fixed at larger ends. Take the Young's value of Young's modulus is 2 into 10 raised to 5 Newton per mm square. So given data, mostly in our questions the diagram is given or may not be given. So therefore, here we go to draw the diagram. So in our questions, there is a two end. One end is area 2 cm square, that is smaller end, and another one end is 3 cm square area, that is larger end. Therefore, here we go to draw the taper, join these two ends, and the diagram is finished into taper bar element because the axial load is act in the smaller end. So in our question, it is given the given element is two finite element. Therefore, this taper bar is discretized into two element. For simplicity, here I go to transform this taper bar into stepped bar, and that stepped bar is discretized into two element 1 and element 2. So element 2 have two nodes, node 1 and node 2. Element 2 have two nodes, node 2 and node 3. So area at node 1, here the cross-sectional area at node 1 is given, area at node is given. So area at node 1, that is larger end 3 cm square, area at node end, that the smaller end is node 3, that is A3 equal to 2 cm square. Total length is 100 mm. Therefore for first element L1 equal to 50 mm, second element L2 equal to 50 mm. Area at node 2 is not given, therefore area at node 2 is A1 plus A3 divided by 2. 3 plus 2, 5 divided by 2, that is 2.5 centimeter square. Then next we go to find the average area of element 1. Average area of element 1, A1 bar, it is denoted by A1 bar, average area of element is A bar, so average area of element 1 is A1 bar equal to area at node 1 plus area at node 2 divided by 2. That is area at node 1 equal to 3 and area at node 2 equal to 2.5 divided by 2, that is 5.5 divided by 2, that is 2.75 centimeter square. Then centimeter square is converted into millimeter square because Young's modulus value is 2 into 10 raised to 5 Newton per mm square. So this centimeter square is converted into mm square. 1 centimeter square equal to 100 mm square. Therefore 2.75 centimeter square equal to 275 mm square. Then average area of element 2, A2 bar equal to area at node 2 plus area at node 3 divided by 2. Because element 2 have two nodes, node 2 and node 3. Therefore, average area of element 2 equal to area at node 2 plus area at node 3 divided by 2. A2 bar equal to area at node 2 equal to 2.5, area at node 3 equal to 2. Therefore, 4.5 divided by 2, that is 2.25 centimeter square. 1 centimeter square equal to 100 mm square. Therefore, 2.25 centimeter square equal to 225 mm square. The tensile load at node 3, because no axial tensile load is act in the smaller end. That smaller end node is 3. Therefore, tensile load at node 3 equal to 50 Newton. Young's modulus for two elements is same, that is E equal to 2 into 10 raised to 5 Newton per mm square. So, on our question, aim is to find the stress distribution in uniformly tapering bar sigma 1 and sigma 2 equal to what? Solution. So in our question, listen carefully. In our question, mass density or weight density is not given, and this is a vertical taper bar. Vertical taper bar self-weight is considered, or sometimes self-weight is neglected. So in our question, here we go to consider self-weight or neglect self-weight. That is our question. Consider self-weight or neglect self-weight? Neglect self-weight, because in our question mass density and weight density is not given, therefore our question self-weight is neglected. If mass density or weight density is given, then the self-weight is considered for vertical bar type element. So for element 1, F1, F2 equal to A1 bar E by L1, matrix of 1 minus 1 minus 1 minus and 1, matrix of U1 U2. So finite element equation we already we know, that is F equal to Ku. F is the body force vector, K is the element stiffness matrix, and U is the displacement vector, and that F equal to Ku is transformed into F1 F2 equal to A1 bar E by L1, matrix of 1 minus 1 minus 1 1 U1 U2. Substitute all the corresponding values. A1 bar equal to 275 mm square, Young's modulus equal to 2 into 10 raised to 5 Newton per mm square, L1 equal to 50. Simplify these values, the value yields 11 into 10 raised to 5. For assembled purpose, here I go to multiply this 11 inside the matrix, therefore 10 raised to 5 into matrix of 11 minus 11 minus 11 11. For element 1 there is two nodes, node 1 and 2, therefore here I put the value 1 and 2 over the matrix. For element 2, similarly for element 2 have two nodes, node 2 and node 3, therefore F2 F3 equal to A2 bar E by L2, matrix of 1 minus 1 minus 1 1 U2 U3. Substitute all the corresponding values. A2 bar equal to 225 mm square, E equal to 2 into 10 raised to 5 by Newton per mm square by 50 L2, 1 minus 1 minus 1 1 U2 U3. Simplify these values, the value yields 9 into 10 raised to 5. For assemble purpose, here multiply 11 into 9 inside the matrix. For 10 raised to 5, 9 minus 9 minus 9 9. For element 2 have two nodes, node 2 and node 3, therefore write 2 and 3 over the matrix. Next step, assemble element 1 and 2. Finite element equation 1 and 2. Simply write F1 F2 F3 equal to, so total 3 nodes, node 1 node 2 node 3, write over the matrix. Then look at first element, 1 and 1 the value is 11, therefore here we go to write down 11. For 1 and 1, here write 11. For 2 1 that is minus 11, therefore here we go to write down for 2 1, here we go to write minus 11. For element 1 there is no 3 1, for element 2 also there is no 3 1, therefore simply we put dash. Then for element 1 and 2 the value is minus 11, 1 and 2 value is minus 11, 1 and 2 the value is minus 11. 2 2 for element 1, 2 2 equal to 11, therefore 2 2 11. Come to the second element, element 2, 2 2 equal to 9, therefore here we go to write down 9. 3 2 equal to minus 9, therefore write minus 9. There is no 1 3 for element 1 and 2, therefore simply we put dash. 2 3 equal to 2 and 3 equal to minus 9, therefore here we go to write down minus 9. 3 3 equal to 9, therefore here we go to write down 9. After simplify all the values, final assembled equation will become F1 F2 F3 equal to 10 raised to 5, 11 minus 11 0. For dash simply we put 0, minus 11, 11 plus 9 20 minus 9. For dash simply we put 0, minus 9 and 9. U1 U2 U3. Next step, apply boundary conditions. The larger end is fixed, that larger end is node 1. Node 1 is fixed. In the fixed end there is no displacement, therefore U1 equal to 0. Self weight is neglected because here the mass density or weight density is not given, therefore F1 F2 equal to 0. F3 equal to 50 Newton, that is given, that is the axial tensile load is act in the smaller end, that smaller end node is 3, therefore F3 equal to 50 Newton. Substitute all the values in the assembled global finite element equation. F1 equal to 0, F2 equal to 0, F3 equal to 50. U1 fixed end is fixed end is there is no displacement, therefore U1 equal to 0, therefore here we go to strike out the first row and first column of the matrix, therefore U2 and U3 is not equal to 0. So this matrix form is transformed into simultaneous equation form. that is 20 into 10 raised to 5 u2 minus 9 into 10 raised to 5 u3 equal to 0. Minus 9 into 10 raised to 5 u2 plus 9 into 10 raised to 5 u3 equal to 50. After solve this equation, the values yields u2 equal to 4.545 into 10 raised to 5 10 raised to minus 5 mm, u3 equal to 1.010 into 10 raised to minus 4 mm. Then next we go to find stress distribution. So for element 1, sigma 1 equal to E into u2 minus u1 by L1. E equal to 2 into 10 raised to 5, u2 equal to 4.545 into 10 raised to minus 5, u1 is fixed and minus 0 divided by L1 equal to 50. After simplify these values, the value yields sigma 1 equal to 0.1818 Newton per mm square. For element 2 have two nodes, node 2 and 3, therefore sigma 2 equal to E into u3 minus u2 by L2. E equal to Young's modulus for both elements is same 2 into 10 raised to 5, u3 equal to 1.010 into 10 raised to minus 4 mm and u2 equal to 5.545 into 10 raised to minus 5 by 50. After simplify these values, the value yields sigma 2 equal to 0.222 Newton per mm square.